Hello, and welcome to the Casa XPS software demo for analyzing your XPS data. The first thing to do is to download the Casa XPS Zip folder off of the link on the Canvas page. There is a button you have to hit to download the whole folder. Don't just grab all the individual things inside. Once you download it, you'll want to unzip it somewhere you can find it easily. For this demo, I put everything on the desktop to make it easy to find. And then the first thing we need to do is activate it. The nice thing about this software is you don't actually have to install anything. You just have to have the folder there. So you could even put it on like a flash drive, and whatever computer you plug it into, you'll be able to use it. As far as I know, this only works on PCs, not Macs. So just an FYI. Like I said, the first thing we want to do is activate it. So I'm going to open up the folder, and what we click to run it is just this Casa XPS.exe. One thing you can do is right click and create a shortcut to run it easier if you want to store it somewhere not on your desktop. So we'll open up the software, and at the top of yours, when you first open it, you'll see it says demo license on the very top bar of the window. So that's what we want to get rid of, is that we want it to look like mine and say WWU site license. If you have the demo license, you can still do all the workup, you just can't actually save it. So it's really frustrating to have to keep doing the workup multiple times if you have to go back and look at it again. So that's the reason why you'd want to activate it. You can activate it at any time. If you've already started looking at stuff, you can activate it and then be able to save it. To activate it, hit the Help drop-down, hit About Casa XPS. This window will pop up, and the username and license number should already be input for you. If they're not, go back to the Casa XPS folder, and there's a text file that says Casa license. You can copy and paste those values, but it should auto-populate. Then you'll hit Update License. It'll say License Accepted, and then when you close this window, it should switch to this H406 WWU site license. And then the software is activated, and you actually don't have to activate it again on that PC. If you are doing the flash drive portable version, then you'll have to activate it on any PC that you plug it into every time. So I'm going to show you a few features of this software on a demo data file. So this is not the data for your lab, for your PDMS samples. This is just to show you the basic functionality of the software, and then you'll have to apply it to your data set. The sample data file, so to open a file, it's pretty straightforward. File open, and I've saved this one on the desktop. This uses .vms files. So when we open the file, you can actually expand this window, makes it a little bigger. In the middle, it's nicer to see. The axes we have on the y-axis, we have counts per second. The software automatically puts a scaler on it to make the numbers not so long, give you more space. So you can get rid of that if you want, but it's not really important. So these numbers times 10 to the 3 are your actual counts. On the x-axis, we have binding energy, which is plotted in the customary format of high to low. So high on the left, low on the right. That's customary for XPS due to what we're actually measuring in the instrument is kinetic energy, which would be low to high. And when you convert it to binding energy, it ends up being high to low. So this is kind of a holdover from when they originally developed this technique, but it is the customary way to plot it, and you'll want to do that if you plot it on your own, which I'll show you how to export and plot it later. Some of the buttons at the top, which are the main buttons we're going to use, are currently grayed out. The only reason for that is because my mouse is for some reason clicked over in the data pane. If we click on the plot itself, you'll notice a bunch of these buttons are now accessible. So just in case you can't access them, try clicking on the plot first. A couple useful things are just zooming. So if we want to zoom in on a peak, we drag a box. If you click outside the box, it'll just go away and nothing happens. And then clicking inside the box will cause it to zoom in. And then up here, there's these two arrows pointing towards each other. It says reset, or the hotkey is F4 to reset your view. We can get our crosshair position, so the position of our mouse, we can get if we click and hold. So if I click and hold, at the very top right of the plot, the current crosshair position shows up. So up here when you click and hold is the current crosshair position. That's useful for a couple things. And that's kind of the general gist of it. I'll be calling out what buttons, kind of what they look like, and giving you the hotkey. I don't know how difficult this will be to see on your own computer. I can't actually. I tried making everything bigger, but it doesn't seem to work for this software. So the first thing you want to do when you open up a new data file is do your carbon correction. So it's almost guaranteed that you'll have carbon, especially PDMS actually has carbon in it. But even a sample that doesn't inherently have carbon usually has environmental carbon, dust, a fingerprint maybe, or something on it. And that's actually used to correct the binding energy to make sure that it's at an accurate position. Having the binding energy at an accurate position is useful for identifying peaks. If it's off by a few EV, it can make it a little trickier to identify what element that peak belongs to. And so from experience, I know that carbon is the one over here near 280. So I'm going to zoom in on that. I'll show you also in a minute the library function where we can actually have it pull out from the saved library and this built into the software. We can pull out the positions of all the peaks for whatever element you want to look at. So like I said, I know that carbon is around 280, and it wouldn't be hard to figure out if you were not familiar with that fact. So like I said, we need to correct the carbon for a reference value, to a reference value. So carbon's used because it's everywhere unless you're being very meticulous, clean room style stuff, or etching your sample before analysis, like in the chamber. You're gonna have carbon, and it's actually handy to use it to correct for this purpose. The correction needs to happen for multiple reasons. So your sample is PDMS, which means that it is electrically insulating. So we're doing a technique that ejects a bunch of electrons, which will cause it to build up a charge on the surface. We do use charge neutralization, a charge neutralization gun to try and negate that effect. But it still means that we're not going to have an accurate value either way we did it. So the first thing we want to do is actually get the current peak value for the carbon. I'm going to zoom in again. The simplest way to do that is to just click at the top and hold and get this as 280.5032. And then a reference value, which I don't know if Dr. Pastel or Dr. McGrew are going to give you a reference for this, but you could go find it on the NIST XPS database online. But a reference value for carbon is 284.6 EV, and we had 280.5032. So to do the carbon correction, we're going to go up to the processing tab. Also F8 is the hotkey. It's an arrow, two arrows pointing to the right with a square in between, black. So clicking that will bring up the processing window. The processing history will have nothing in it because we've done nothing. And moving over to the calibration tab, this is where we're going to put in our measured value of 280.5032, and then the true value is 284.6 EV. If you've already laid down some regions and components, maybe you have some familiarity, maybe you are skipping around in this demo, you'll want to check these boxes before you apply the calibration. It actually doesn't hurt to check them if you have nothing like we currently do, so it actually won't affect anything. And then we're going to hit apply. Make sure you only hit apply once, because if you hit it multiple times, it will apply it multiple times and it'll keep shifting it. Back to the processing history tab, we have one line that says we calibrated it. So M equals measured, A equals actual, just telling you what the calibration was. If you accidentally click it multiple times, or you think you did it wrong, or you want to redo it, you can just reset all, or you can just hit remove on a few if you have multiple lines, or just the one, you can remove it and try again. So that's all we need for that window. We can close it and be done there. The next step is to do elemental ID. So there's some things that I'm assuming that you were taught in class about the XPS technique itself. The main thing being orbital peak ratios, and the fact that all the peaks have to be present. But I'm going to do a quick little rundown on this, just to make sure that we're all on the same page. It's just going to be a couple minutes, if that, of chatting about why we do certain things for peak identification. So one of the important things about XPS is that the peak area ratios, or the peak height ratios that you look at on the spectrum, are not indicative of the relative concentrations of that element within the sample. So if we had two peaks, say one for carbon, one for oxygen, and they were identical in height and area, that actually they do not have equal concentration in the sample. So there is something called the ionization cross-section for a specific element, and in this case they're just showing uranium as an example. The ionization cross-section, the definition of that is a probability that a given ionization event will occur. So just because you have equal amounts of two elements in a sample does not mean that they are going to ionize the same amount of electrons are not going to be ejected by the X-rays. But luckily for us, that's a pretty standard event, and it's easily calculated by physicists in the past who developed this technique. And so there's actually a giant table, commonly called a Schofield table, that is full of these correction values that we can use to make sure that we get accurate concentrations. So this is pure uranium, and this is kind of a sideways spectrum. So here's EV on the Y from 0 to well over 1,000. That's higher than we can analyze. We only go to 1,000. 0 EV is the Fermi level, and so they just are kind of showing this more like a potential energy diagram. But if we scanned pure uranium, the peaks that we would see would have these relative intensities. Okay, even though it's pure uranium, and even though all the electrons that gave us these peaks came out of uranium, we're still going to have different intensities of peaks, even within the same orbital. So you can see there's a 4f7 halves, a 4f5 halves that have different intensities. So not only can we use the positions of the peaks to identify what element there is, we can use the intensity. We also need to use the correction factor known as the relative sensitivity factor to correct for the difference in area between not only peaks within an element, but peaks between elements. So that might make more sense when we get to the quantification section. For all orbitals besides S, so P, D, and F, there are two peaks observed. It is quite possible that the peaks are so close together that they kind of look like a single peak, and I actually have an example of that I will show you. The peak area ratios also have to follow certain rules. So for P, D, and F, the ratios of those peaks have to follow these rules. So for P, the 1/2 has to have half the area of the 3 halves. For D, it's 2 to 3, and for F, it's 3 to 4. So if you have a doublet and you're trying to identify what element it belongs to, it's very unlikely that you're going to have trouble if you can figure out, is it a P, is it a D, does it belong to an F orbital, then you can look at the table of what elements have peaks in that region, and it'll help you identify it. So we looked at the uranium, but it was kind of sideways. This is an example of a pure gold sample. And so you can see the drastic difference between peak heights, even though these are all from the same gold. So it's kind of interesting and definitely helpful for our purposes. You'll also see Auger peaks in photoelectron spectroscopy. So Auger peaks we can't use to do quantification, but it can be helpful to identify an element. So sometimes they're annotated differently. It depends on what system you're using. So in here they're doing it NNN and NNV for identifying those Auger peaks. But there's other ways of annotating it. The point is that you can use them to identify elements, but other than that, they're not going to be useful. So trying to identify the elements in this sample. So we're going to kind of treat this as an unknown, pretending I don't know what's in it. But the fact is that you should have an idea of what's in your sample. So it should be pretty easy to narrow it down. And maybe you have an unknown peak or two at the end that this process will help you with. So we're going to open the library window, which is also F10. It has a little black shape of a periodic table with red letters that say lib on it. Like I said, F10 also. You can leave this window open as long as you want and still open other windows or do other stuff. So it's actually quite a helpful window to look at. The first tab that we use is the element table. The element table is, I'm going to scroll real quick. This is a huge table which has all the elements and the positions of all of their peaks. So not only like each element, but each orbital within that element and where its peaks are positioned. And then the RSF, which is the third column, or I guess technically fourth column, that's the sensitivity factor that you use to correct your areas to do your actual quantification. So this can be helpful to pull out those sensitivity factors. I'll show you another way to pull them out later also, so there's a couple ways. The handy thing about this table is that you can click. So if I'm looking at this carbon peak, I can click on it and it will take you to the range in the table that contains the position you clicked on. So we clicked around 284 and it took us to the 284-ish range. So you can see carbon's right there. Carbon has an RSF of 1 because carbon's actually what all the RSFs are normalized to. So if you click on an element from this table, it will plot all the lines on the graph, on the spectrum that element has. So carbon only has one line that's useful that's in this range. If you click it again, it'll go away. But if I just randomly decided like terbium, you'll see all the lines. Another nice thing is that it plots the lines relative to each other. So the largest peak appears to be terbium 4D, and then terbium 4P, and so on. It also plots the Auger lines as just a red line that takes up the whole y-axis. Clicking on it again takes it away. One thing is that the 0 to 30, 0 to 50 range in binding energy is kind of useless for identification of elements just because most elements have something right near the Fermi level, so you're gonna have just tons of stuff down there that'll make it difficult. So this is one way of looking around at elements. It's actually more useful later. The second tab is the periodic table. This is much more simple. You can just select an element. So like I had before terbium, you can click on it, all the lines pop back up, or you can deselect it. A useful function here is find peaks, and the software is going to just look around for all the peaks that it thinks it can identify. So if I hit find peaks right now, a whole mess of stuff pops up, and don't really look at the plot right now, mainly look at the periodic table and look at what actually makes sense to be in here. So dysprosium, I don't think we have in here. So if we hit clear all elements and just pull up that one, we can look and see, do the peak lines match? Now remember, all the peaks have to show up and all of them have to be at the proper location. So we have dysprosium popping up with a peak around 155. That's the peak that the software must have been aligning it to, and the other peaks don't seem to show up. So for now, I'm going to guess that that's not one of the elements in our sample. If we hit find peaks again, we'll look at palladium and gold next. So if we hit palladium, it appears that it's lining up palladium with this peak at 336, which is actually pretty poor alignment because you should see the 3/2 peak, and that's quite off there. It's lining up the 3p over here to this peak, but we don't really see the others. I know from experience that this peak here is probably oxygen, so I'm guessing that palladium isn't lining up very well. And then gold. So if we hit gold, it looks like we have the 4F peaks showing up actually pretty well. We have the 4D peaks showing up pretty well. And it's hard to say for this 4P peak because it's right after this large peak. And after a large peak, you usually get this little hump, which is your change in baseline, which can make it difficult to identify. So that one's just tough to say. And then these other peaks up higher, the 4P 1/2 and the 4S, are just likely too small for us to see. So I did say that you need all the peaks to show up, but if you have something, say gold, that's like 5 or 10% concentration in the sample, then it's going to be quite difficult to get the smaller peaks to show up above the noise. Now you should be able to eventually, if you just scanned for a really, really long time, you should be able to lower the noise and increase the signal. But if you have several other peaks that line up, it's not really necessary. So if we have fine peaks again, I think we ruled out dysprosium, palladium. Let's look at yttrium and beryllium. So beryllium only has one peak, and it doesn't line up. So not really sure why they chose that. Yttrium, the major peaks are in this little hump after the carbon peak, but the pretty large also, 80% of the height of the largest peaks, the 3D, don't line up at all with anything. So I think we're going to rule that one out also. Now we have carbon, nitrogen, oxygen, and chlorine. So I think we successfully said that we have carbon. There's only one peak. Nitrogen looks like it lines up pretty well. We only have one peak. Oxygen, we only have one photoelectron peak. Up here, oxygen does have a peak down in the low end, but again, it's hard to use that for identification. But it does have an Auger peak up here near 984, which lines up pretty well with this peak here. So I think oxygen's a slam dunk there. And then chlorine was the other one. So chlorine pops up around 200 and up here at 270. Those seem to line up actually. So I think chlorine's pretty good. So if we put the elements in that we think we have, so carbon, nitrogen, oxygen, chlorine, gold, we can then look for peaks that haven't been identified, which it mainly looks like there's this peak here at 155 and this peak here at 104-ish. And so this is kind of where we would actually use the element table to try and see what elements fall in that range. I'm going to try and remember those two peaks and clear the rest of them just to declutter the screen. So if I click on this higher one, arbitrarily deciding to choose the higher one, I don't know, 155-ish, we'll look and see in this range. So if it's around 155, you can usually look plus or minus 5. I mean, that has nothing to do with it being around 155. But if you're looking you can usually do plus or minus 5 EV, just because there could be a lot of factors that change where the peak shows up, like maybe your carbon was done a little incorrectly. That's not usually the issue, but something that could make the peaks off is like the chemical environment around that element. So let's say that you have something super electron withdrawing, it should shift it to a higher binding energy. If you have something super electron donating nearby, it can shift it to a lower binding energy. So plus minus 5 EV is a pretty good buffer there to try and look around. So looking right around the 155 range, it looks like dysprosium. We actually already ruled that out. Going up higher, we have yttrium, again, ruled that out. Gallium, we haven't looked at that one yet. If we click on it, we see that the Auger peak is missing. The 3P peaks actually line up okay. They should be much larger though. So if you look at the 3P peak up here versus the 3S peak down here, it looks like the 3Ps should be about 3 times larger. So those ratios are pretty off. We'll keep that in our back pocket. Bismuth just doesn't seem to line up. We should have these 4D peaks up here. They're quite large. They should be quite large. Yttrium, we already said. Bismuth again. And now we're kind of outside of our buffer. Going down in EV, we have radon. The largest peak in radon doesn't show up at all. So if you look at the relative intensity between this, which is quite small compared to this peak should be huge. So I'm not thinking that's likely. Then we have antimony. Antimony doesn't appear to be a good match. We should see the 3p3 halves up here. We should see something a little different near the oxygen because there's actually 2 peaks that are on either side of oxygen. And then looking down a little lower, we have silicon. Silicon only has peaks down on the lower end, so I'm going to zoom in there. Let's see, for silicon, it actually has a peak at the 155-ish and the 103-ish area, which is actually kind of nice. It lines up at least. The peaks are there. The ratios don't seem like they're off. They're fairly similar in height. It's hard to say for sure right now with the baselines shifting. And we're about, let's see, so I'm just clicking and just approximating 103.5-ish to about 99. So we're about 5-6 EV off from a reference value. And on the 2S, 55, yeah, we're about 5 or 6 EV off. So the fact that they're both off about the same amount from each other is actually pretty good evidence that these do line up with silicon. So this was kind of being treated as our unknown peaks because we couldn't easily identify them. It turns out that silicon is the answer, and it was contained in the sample originally. So this was a researcher's sample that they brought over, and they did know silicon was in there. So, but we did deduce it. I showed you how we deduced it, so you could actually get an idea of how we would do that. Zooming back in, sorry, I forgot to show you that this is an example of where the P peaks, there's 2 of them, are so close together that it looks like one peak. That's not uncommon at all. So, carbon, nitrogen, oxygen, chlorine, silicon, what do we have? Gold. And I think that was it. Those are the peaks that we've identified. And it looks like we have caught them all. Peak identification or element identification can be tricky, so definitely ask questions about this part if you're stuck on anything. Remember, all the peaks have to be there, but smaller peaks can be buried in the noise, so keep that in mind. Now that we've finished our element identification, we will want to do integration. So we actually use the integral of the area under the peak to get the percent concentration. We don't use the peak intensity as certain analyses might. So there's two ways to do the integration, and one of them is pretty simple, and we'll start with that, and the other one is a little more complex, not crazy, and we'll show you that too. So I'm going to clear all the elements off the screen just so that it's a little cleaner, and I'm actually not going to integrate every single peak, and I'm not actually even going to integrate for every single element. I'm just going to do a few of them just so you get an idea about it, and then you can apply it to all yours. So remember that you only need to integrate one peak for each element. So if, like we showed that silicon has two peaks, right? Or I guess one is technically a doublet, but two main peaks that we can work with, you only have to integrate one of those. So ideally, you're going to pick the peak that is by itself. If you have a choice between if one of them is overlapped, you're going to choose peaks that are by themselves, and you're going to choose the peaks that are supposed to be the largest. So out of these two, the 2s should be the largest according to the RSF. So these peak intensities, the relative peak intensities, are dictated by the RSF. So like gold is a better example for that. So if we looked at gold, ideally we would be integrating the 4D region because they're supposed to be the largest. If those happen to overlap with some other elements that we had, then we would try and move down to the next one, which would be the 4F, and so on. Also, you want to just try and pick the ones that look the cleanest. In our case, we don't have to really worry about that. Most of our peaks are not overlapping with each other for different elements, but you may run into that. So the first method is going to be used when you have peaks that don't overlap at all. So that's the method we're going to go with right now, and then I'll show you the more advanced method after that. So to do the quantification, you're going to go to the Quantify button, which is also F7. It's directly to the left of the processing button. It looks like a little spectrum with like a greenish bluish bar on it. And again, you can leave this window open as long as you want and put it off to the side. So we're only going to use the first two tabs. So the first tab is the first way for integrating. The second tab is for the second method. So in the first tab, there's currently nothing because we've done nothing yet. So I think we're just going to do carbon, nitrogen, and oxygen as the examples. So I'm going to zoom in on carbon first. So I'm going to create a region. So that's what is in the regions tab. You hit create, and you'll get this bluish spot. The whole screen currently is bluish, but it's actually like a separate region on the plot. So it's very hard to see, I'm sure, on the video, but if you grab all the way to the left, there's these tiny little gray bars, and those are what you use to resize the region. The black line at the bottom is our background, and so the default background is not very good. It's called the U2 Togard. I don't know the proper pronunciation, but if you type in right there, Shirley, and then make sure you hit enter, you'll see when I hit enter, the background changed. So once we've changed the background type, any new regions we create will have the Shirley background, so you don't have to worry about it after the first time. And so we're going to drag this to include only the carbon peak, because anything that is above the background, so like if I had the background here, this little part here is going to be integrated. So anything above the background in this method gets integrated. So even though this is actually pretty well lined up with the background, we're still going to shorten that up so that we only integrate the carbon peak. One handy thing here is that you can pull the RSS this way. So the first row is the name. So I would probably call this the carbon 1s because it is the carbon 1s. But a handy feature is that if you type in pound, just pound, and then the orbital, the element and orbital, it will pull the RSF from the table when you hit enter. Now in this case, the default RSF was 1. So if I type in pound oxygen 1s, which is the wrong element, but I just want to show you, and hit enter, it pulls it. It's 2.93. We're going to go back to carbon, because that's what this actually is. Pound carbon 1s, make sure you hit enter. Boom, it pulls it out, RSF of 1. So at this point, since I'm starting my quantification, this is when I'd pull up my spreadsheet to do the actual math. It's not difficult math. And I would set it up like this, you know. I'd have my sample name, and then I'd have element, orbital, RSF, area, and then corrected area, and then percent concentration. So remember that this is atomic percent. This is not mass percent. This is comparing one atom of one element to one atom of another. So we started with carbon, 1s orbital, has an RSF of 1. The area is actually pulled from this row here in the region. So it has an area row. So it's 53,830.5. So 53,830.5. The corrected area, so to correct these, we actually divide the area by the RSF. For carbon, it's the same, but for other elements, it's definitely going to be different. So the second one we're going to do is nitrogen 1s, and we'll pull that RSF. So you can leave the quantification window open. Like I said, we're going to zoom out. We're going to zoom in on nitrogen, which is at 400. I'm going to create another region. We're going to name it. So pound N 1s, hit enter. So apparently the RSF for nitrogen is 1.8. And then we're going to drag the edges of this. So this one's a little smaller, so there's a lot more noise affecting our peak integration here. So ideally the background splits the noise in half, right? That would be random about the background. That would be the best choice. It is kind of tricky doing it. But if you extend this, anything, even these tiny little blips of noise that are above the background, anything is getting integrated. So with this method, you want to keep it as small as you can. There is some inherent error in this method because of the fact that you're manually doing this. So it has an RSF of 1.8, and the area for this one is 4954.7. All right, let's line up these. I'm not worrying about sig figs. Make sure you keep track of sig figs. And then I think the last one we'll do will just be oxygen 1s. We already know that that's 2.93. So we'll go back to our software, zoom out, zoom in on oxygen, maybe a little better, and then create another region. Just a note that whatever your view is when you create the region is going to be the view, is going to be the width that the region is. So if I was zoomed all the way out and I created one, it would be from 0 to 1,000. So that's personally why I zoom in first. So this one is 24,420.8. So like I said, you'd want to do one for all your elements that you're interested in. I'm not going to do it for gold and silicon and stuff just because it's repetitive. Your percent concentration is simply your corrected area as a percent. So we're going to do equals sign, the corrected area for carbon, and then we're going to divide it by the sum of all the areas, right? So highlight these three. A handy feature for Excel, if you're not familiar, is to hit F4, and whatever the cursor is near, it will change it to a concrete reference. So there you go. So that means, if I hit enter, when I drag this formula down, that if you watch as I arrow down, the sum part doesn't change, but the numerator does. So we can confirm that we got the right value, and it adds up to 1. So you can convert those to a percent if you want, using just the percent button in Excel. Again, monitor your own sig figs. So from this, it looks like we have approximately 83% carbon, 4.2% nitrogen, and around 13% oxygen. And don't forget also that this is highly surface sensitive. So this is around 3 to 10 nanometers of the surface that you're actually able to probe. That's how deep you're able to probe. So I'm going to minimize this. So that was method 1. Remember, add all the elements that you actually care about. Method 2 actually requires method 1 to be done. So you have to actually have created a region. I'm actually going to create a region for silicon for the 2P peaks. So I'm going to create a region, and I'm going to deconvolute these 2 peaks. So this, I told you that the second method, which is in the components tab, is for deconvoluting 2 peaks that might be overlapping. In this case, there's the p orbitals, and there are 2 peaks within this. Creating a component, so there has to already be a region. Once you're in the component tab, you can't edit the region. Sorry, that was bad clicking. Yeah, once you're in the component tab, you cannot move the region. So it's actually nice because you don't accidentally move it all around. So if I create a component, you'll see it creates this peak here. So this peak, the coloring isn't that great. So it's like a purpley magenta-y color, and the data is like maroonish. So maybe on your screen it's not that easy to see. Let me mess with the display thing real quick and actually, there's the display settings button. You can mess with settings, but you're probably going to be exporting this to Alright, so I got it to show up a little better, just thicker lines on the display, so you might be able to see a little better. So we have this pinkish one. If you click on the top of the peak, you can change just the height. And if you click on the sides, about the full width half max point, then you can get the peak to go narrower or broader. There's not actually a lot of reasons that you need to be manually editing them, moving them around, but sometimes it's just handy to make things look a little less complex and cluttered up. So if the button to have the software fit the peak, the component to the peak is this fit components button right in the middle down here. And if we hit that, it's not going to do a very good job, and that's probably because there are supposed to be 2 peaks in here. So if we create another one and fit that, clicking it a few times is actually pretty helpful. Then it will, sorry. Upon trying to move peaks, you will often accidentally zoom. It's just a fun way that their software is designed. And so if you keep fitting it, if you click it a few times, it'll get to a local minimum. And then we can hit the residual on button is directly below quantify. And that will show you the residual for your fit. And so you want it to be random about the noise. This fit isn't actually that great. But so things that we would do if we wanted to make this fit look better would be to constrain the fit. So the peak on the left should be the 2p 1/2, and the peak on the right should be the 3/2. So the one on the left should be half the area of the one on the right. So if you click on the column of the component, it will actually tell you which peak is which, so you don't forget. So you have an area row, and then you have an area constraint row. So if we take A, delete the area constraint, and no equal sign like Excel, just type in B times 2. So that's saying that A is required to be twice the area of B. And if you're constraining that, you also need to constrain the full width at half max to be the same. So this would be B times 1. The reason for that is that when you're constraining these 2 peaks to each other, you're saying that they're from the same exact type of silicon. So therefore, they must have the same full width at half max, because they should be from the same exact atom is basically what you're saying. So now if we fit these, we can see if we're going to get an actual decent fit. it turns out that it's not going to fit well. The reason for this is because there's actually two types of silicon in this system. So we actually need a doublet of these doublets. We need two of these doublets. So what you can actually do is hit copy all and then hit paste. And now you have A, B, C, and D. And they currently overlap perfectly because they are the same. And hitting fit on that actually makes things quite weird. So this is why this is a little bit more of a complex method. The other thing that we need to use is we need to use the position constraint. So the smaller peak should always be on the left, so at a higher binding energy. And there actually is reference values for silicons, the silicon 2p orbital separation. So if we pull up a browser and search for the NIST XPS database, you can click, it's always the first link, and you'll hit retrieve data for element. We're looking right now, so binding energy is really good. They have references if you need to find where an element has peaks, but we're looking for doublet separation right now for silicon. And then they only have the one for the 2p because that's kind of the only doublet that's in the normal range of scanning. And then you can see that it's right around 0.6. So these are actually experimental references. If you click on details, it even gives you like an author, so you can use these in your reports as references. But it looks like 0.6, plus minus 0.02. They even give you uncertainty. That's great. We can't use that, unfortunately. But so in this case, we're going to go A. We're going to constrain A to B again. And in the position constraint, we're going to say B plus 0.6. Nope, sorry. B minus 0.6. I was going the wrong way. And then the same thing for C. So we're going to go C is going to be D minus 0.6. Always make sure you hit enter when you're doing these because it doesn't accept any of the changes unless you hit enter. So again, clicking it a few times, getting it to actually find the minimum. It seems like we got a bit of a better fit. We didn't actually have the position constraint when we did our first fit, so I'm going to actually cut out peak C and D and see if we can get this to shape up, because that might have been what we needed on the first go. No, it appears that that was not the case. I'm a little confused why it's not. All right. So again, with the manually moving them, one thing that you'll notice when you're doing this is that the one that's constrained, you can't actually move. So A is constrained. I can't move A, but I have to move B because A is reliant on B. So just so you know. All right. So this is actually a pretty good fit here because of the low resolution nature of a survey scan, and also the fact that we didn't get great signal to noise on this. But this is actually a pretty good residual, and the fit looks pretty good. So what you would do after you fit this is you'd take the area from the area row, and if you wanted all the silicon, we'd in this case add up all 4 peaks. But if we wanted to, if this was deconvoluting 2 different elements, then we would just take the elements out that we wanted. One thing that you really use this for is, so say that as a reminder, gold has 2 peaks for the d orbital here. So if we had, let's say the 3/2 peak was free and the 5/2 peak overlapped with something, and we wanted to get the something. Let's pretend it's carbon, even though they're far apart. If we wanted to get the carbon out, we could constrain the 5/2 peak to the 3/2 peak so that we make sure that our 5/2 peak is accurate, and then we know that what's left over is carbon. So that's another important usage of that method. So again, you're going to put that into your area part of your spreadsheet, and then use that to calculate your concentrations in the same way. The last thing you might want to do, or probably will want to do, is export the data so that you can plot it in a different program. Up right under the select dropdown, there's one. If you hover over it, it says Save Tab ASCII to Clipboard. And if you click that, it has all these, it's not very complex, but kind of complex looking columns set up. If you hit copy all to clipboard, then you can paste that into an Excel sheet. And then what you have here is you have the first one is kinetic energy. So that one you won't use. That is the kinetic energy used to calculate the binding energy. Our binding energy is no longer starting at 1,000 because we did our carbon correction. And so this would be your x-axis. This first one is your y-axis for just your raw data, and then all of these other ones you'll have to plot individually, but they're all like your background for your regions, your carbon region. So it includes all the stuff. It even includes your component fits somewhere in here. So that's the best way to export it, and then you can, put it in, plot it in Excel, plot it in Origin, plot it in whatever works for you. I think that's about it for the general overview. I know that there was a lot of stuff, but go through again, pause it at sections that you need to. Let me know, or let one of the TAs or professors know if there's a section that you really can't see, and we'll do our best and edit the video and try and make a better spot for that. So good luck.